you just draw in one direction once, and then you draw the same thing for the dry portion in one direction. A lot of people do 8s. 8s are for polishing. You go like this. Don't do that. You will ruin the end face. Don't do that. Especially with arc boards. They're expensive. You just do it once, go down about 2 centimeters, so you just do it wet, and then dry, and it's finished. Okay? So it's quite easy and straightforward. You don't reuse. So if you're using it, let's say one tab, you can use this portion, but the other portion you segment basically, and if you want to have individual ones as well. So they have clean surfaces which are about 1 centimeter by 1 centimeter that you can use for drawing purposes. Okay, the kits come in this format. So we have the cleaning solvent, we have the earbuds for different type of bulkheads, and then we have the lint-free cloth here, and then we have the single ones which are on a big pad, but they are 1 centimeter by 1 centimeter going here.
Excuse me.
Yes. I think you can do about 100. There's 100 slots in there, so you can do 100.
What about the web kit?
We have that one as well. Okay. It all depends on which environment you're using it for. If it is low humidity, we recommend 1 click. Okay, if it is high humidity, we recommend this one, the manual one. Okay, especially with the high humidity because of the salts. You need to really, and this is the 1 click one. So basically, they clean both male and female. Just do a single click, and every click will do 500, or every single one of these will go for 500 cleanings. Okay, so these are also available. It can be used for SC, ST, FCE 2000, various ones. You can use it for LC. Even we have the MPO MTP version. I have the MPO MTP version here, I believe. Yep, here's the one. This will clean 12 fibers in a single shot. So this is the guy that is over there. This one. Okay? And then we have the same kit with the inspector as well. So if you want with the inspector, you can get it as well. But this one, again, you will see it, you cannot document it. If you want to document it, you have to use your camera as well. Okay?
The inspector is for the NPO as well?
Sorry?
The inspector is for the NPO as well?
No, we have a specific inspector for MPO as well. But this is not the one. Yeah, we can inspect all 12 boards. Yeah. It's a little bit hard to work with because we have to, we have available. We have available. Yeah. But for the MPO, I recommend to just do the cleaning, and you should be in good shape because the terminations are all factory made, so they are pretty dark red. I wouldn't worry about that. Okay, now we're going to go talk a little bit about lost length certification, see what we have in store for you there. This is one of the nightmares of fiber optics. There is so many different standards and there's different parameters that you have to figure out, scratch your head, what to do, what not to do. And making the right decision on this proper limits makes the difference between a real pass and a real fail. So you have to use the proper standard test limits, and it is not easy, believe me. You have to, anybody who wants to come to the training courses to understand about all these things, please do let us know and we'll tell you what you need to do. This is a typical small overview of standard-based limits. We have application-based limits for single mode, for multi-mode, for 10 gig, for 100 gig, for 40 gig. Then you have the channel limits, and you have the link limits, then you have the component limits, and then you have the, there's so many variables. And it gets quite confusing when you look at these things. Okay, what are the limits, what are the losses, what are the allowable losses? Should I, maybe I have a link, should I do it on all 300, or should I do it on, maybe on a different standard, maybe, 14763-3, different things are there. So you have to know exactly what standard you need to use in order to get the proper results. Depends on your environment as well. Now, as I said, there is various standards in the ISO Synergix TIA, and anybody who's familiar here with the TIA 568 standards, B123, or now there's C, which is commercial building, then the C2 is for the twisted pair, and then C3 is for fiber optics. And then you have the ISO, which is for customer premises 24702. Then you have the generic cable for industrial premises, so this is for industrial requirements. It's a totally different standard, 764. And then you have the data center, which is 15018. And then for the Synergix is the same way. However, for the testing, for the field testing, when you want to use a field tester, they all refer to the 14763-3 standard. Remember one of the questions I had, how many of you know about 14763-3? It is this one. So it will tell you how you have to do the testing. Okay? Also in Synergix, it refers to 50346, and 50346 again will refer to 14763-3. This is the de facto standard for field testing, which we comply to 100%. Alright? So very, very important to know this. Alright.
So that includes the stringent parameters over the TIA and the Synergix.
They're pretty close, but it is usually the European standard that we follow. And especially in data centers, that's right now the de facto. You have to follow 14763-3. You will see why and where and when. Okay, now, typically, once you want to do a testing, as I said, when you go to higher bandwidth, your budgets are becoming smaller. So you need to, every single DB will have an issue for you. So that means you have to perfectly make sure that all of the contributions from the tool itself, from the losses that it will contribute, is moved out of the measurement. Okay? Because once you want to do a set reference, you will set the reference, but there is a patch cord in between, then there's a connector here, there's a connector here. All these contribute to the performance of your link, and that's not part of your link. So what you do, you have to set reference, remove this portion, and then do the actual measurement. So typically you can see for the 14763-3, it says for fiber 50 micron, the standard losses are 3.5 cubic per kilometer. So for 200 meters, you multiply this for 0.2 kilometers, multiply by 3.5, you get this much losses. Also, you have two end connectors, and the losses for end connectors in the standards are 0.3 dB. And then for the embedded connectors, it's 0.75 dB, and the splice maximum is 0.3 dB. So it's variable. Always remember, when you want to do cabling standards, especially one like the 11801 or TIA 568C3, it's variable depending on your length, number of connectors, number of splices. Your total loss budget is compared to the actual budget, so it's not fixed. In the copper standard, it's always fixed. Whether you're running 20 meter, 30 meter, 40 meter, 50 meter, all the way up to 90 meters, it is fixed. It is not distance dependent. Whereas here, it is the number of splices, number of connectors, all of these will contribute, so it's variable. Okay? Cabling standard. Now, application is a different story. We'll discuss about that later. Okay? Now, this is very critical for you to understand that every single dB in the fiber world, it's a huge loss. 3 dB loss is equivalent of 50% of your power loss. That means if you have 3 dB, 50% of light will go through, 50% will loss. If you go 10 dB loss, 90% is lost, 10% will go through. So making sure that your fiber links are clean and you take the contribution of the tester losses out becomes critical. Alright? And also then we get into something called repeatability and basically uncertainty, which I will discuss later. You will see that. So always for troubleshooting, always verify, make sure the polarity is correct, end phase is good, and you are using the right practices, which is like 14763-3, to ensure everything is done. The other thing that you need to do is, let's say, you will see later on, that even though if your link passes, the entire link passes, but a component or a segment within that link might fail, which tier 1 will not show you. Let's say, for example, if your total allowable loss is 2 dB and you show 1.8 dB on your total loss, you will have a pass. But maybe a coupler in there, which has a maximum allowable loss of 0.75 dB per standard, has a 0.8 dB standard, 0.8 dB loss. You will not see it in a tier 1 test, which is optical loss test set. So what they recommend, especially it is mandatory in the data centers, you have to do a tier 2 test to ensure that all the components are running within the standards. That means your fiber links are proper, your splices are within the standard, and also your couplings are within the standard. In addition to that, if there is any problems, you can rectify it and you can go ahead and identify where the location of the fault is, and then you can rectify it, and then you will increase your budget. So tomorrow when you want to migrate to a different standard, you don't have to change the cabling, which is quite critical. You will see that as we go along. So there's two ways that we can do the testing. One is called optical LSPM, which is light source power meter. The other one is what we call optical loss test set. The difference between the two basically is this one, which here in this test, you have to know a lot, and you have to have at least 10 to 15 years of experience with fiber to look at these numbers and make sense of them. Okay? You have to also here, you have to go and figure out what is the lengths that you have to have papers, you have to have calculations, and manually you have to look at the total loss budget and see the number here and then decide whether this is a pass or fail. However, on the optical loss test set, everything is done automatically. So it will know the total loss budget, it will know the performance, and will tell you whether you have a pass or a fail. And then on top of that, it can do bidirectional testing on multi-mode. On top of that, you can also do two wavelengths at the same time. Here, you have to change your light source every time. Because in the, let's say, multi-mode, you want to do 850 nanometers and 1300 nanometers to ensure that both are proper. Okay, and then you have to do testing from both sides for multi-mode. So this one will automate everything for you and will give you a pass-fail results. Whereas this one, you have to decide what's a pass, what's a fail. And usually most of the consultants will not accept this. They want an optical loss test set result. Alright, now, if you can see here, both in TIA 568C3, they recommend a tier 1 and a tier 2 test. And then in the ISO, they call it a different thing. At the end of the day, it's the same thing. It's called light source power meter for the tier 1 testing. And the other one is called OTDR, or optical time the memory reflectometer testing. The difference between the two is this one is quite accurate, but it doesn't see the losses in the specific components within the link. Let's say a splice or a coupling, as I mentioned before. Whereas here, you can see specific losses for every single component within the link itself. However, this one is less accurate. A lot of people depend on OTDR. They say, okay, OTDR does it for me. I don't have to worry about it. But the result of this one is not that accurate for the entire channel. However, this one is quite accurate. So you have to do both. And also, in order to get your 25-year performance warranty from the manufacturers, you have to do this. And that's what the consultant wants from you. They don't want an OTDR test. And the OTDR test also is a single-sided test, whereas the optical loss test is a two-sided test. And I will give you an example which happened with one of the biggest consultants in this region, in Qatar. And they just didn't know what they were doing. They tested a single link with OTDR from one side, and they were getting 1.76 dB loss. They were testing the same fiber with the same OTDR from the other side, and they were getting 2.8 dB loss. And that's where the confusion comes. How come the same link, one core from one side has a different loss, and the other side doesn't have a loss? Because they didn't use the proper tool. OTDR is for location, finding the location of the fault and to look at the single component performance. Now the advantage that we have over other OTDRs, and this is from even our first generation OTDR, is that we can give you a pass-fail for every single component. The other OTDRs don't give you a pass-fail, they just give you the results. We give you a total pass-fail on every single component within that link. Alright? So, tier 1, as you can see, it's required. Alright? And for end-to-end, it's ideal, as I mentioned before. And we test against the loss limits based on the industry standards for current applications. Okay? Now, let's take a look at, I want to talk about set referencing and the effects of proper set referencing when you do the measurement and also test reference codes. I have a scenario here. I'm going to do a 3-jumper reference, which I will explain later. You will see the next picture what happens. But just remember these numbers. So I have a connection or a company. One is up, one is down, and the total loss is 0.6 dB. Then the other one also, one is down, one is up. That was also 0.6 dB. The other one is both of them are up. There's a 10th of a dB loss. The other one, both of them are down. With the ferrules meet, they're all both down. They're 10th of a dB down. And then there is one which is, one is centered, one is up, which is 0.3 dB down. The other one is down, the other one is centered, and that one is also 0.3 dB. Now, when you do the 3-jumper, so what we do here is we have 3 jumpers, we set reference, we remove this guy, and we put our fiber in the test. Right? Right? Everybody is with me on this picture? Very straightforward. It's a 3-jumper reference. We put 3 chords. We set reference, so we want to take the contribution of these components out of the measurement. We put our fiber link, we remove the middle portion, we replace it with the fiber link under the test. We make the measurement. We take the total, reduce the contribution of this, and we get the total loss of the fiber link. Right? Okay. So let's take a look. Once we do set referencing, remember this north-south, how much contribution did it have? 0.6 dB, right? So it is reflected here. The loss of this one, 2 meters, a 10th of a dB, or 100th of a dB, 0.6 dB, 6/10ths of a dB is for this guy, which is here. This one is 2 meters, 100th of a dB. Then we have this one, which is 0.6 dB, and then the other one is 10th of a dB. So the total is 1.23 dB loss, which I have to remove from my calculation, right? Everybody with me? Okay, now, we put the fiber for testing into the link. Now it happens that this guy, the ferrule for this guy is also up, and the ferrule for this one is down. So we make the measurements, the 2 meters remain the same, so the losses is correct. This guy had a 10th of a dB contribution, 0.35 dB for 100 meter of the fiber link, because we multiply by 3.5 dB per kilometer. Then we have connector 2, which also both down was a 10th of a dB. And then, so the total loss when we add is 0.52. Now we have what we call a gainer. That means if somebody with no experience looks at this, it looks like that you get more energy out of the fiber that you send the light to. So if you have one light, you get 2 lights out. Energy doesn't work like that. It's the other way around. You put 2, you get 1 out. So there's something fishy here. Right? You cannot have a gainer. This is called a gainer. When you add, they don't make sense. So let's take a look at the next scenario. This one, you see that we have done the same thing. The only thing is that, again, the combination of these things have changed. And now, once we do the testing, we get 1.52, and then we redo the testing, we get 0.52. This time we have 1 dB gain. Again, this is the issue. So we do the testing again, which now, the chords are centered. So we do the set referencing with a centered chord, and we get 0.23 dB loss, because remember center to center was how much? A 10th of a dB. Center to center was a 10th of a dB, right? Now, when you do the testing, and this one is up, and this one is centered, you have 3 dB loss, 3/10 of dB, and then here you have 3/10 of dB. Now you can see the total losses is 0.97, and the difference between the two is 0.74. So this now makes more sense. So you can see the effect of the patch cord that we have here is quite critical. That's why you cannot use a regular patch cord. You have to use a test reference cord that is properly tested, certified, and it is designed for set referencing. This is what we supply. Our test reference cords are hard end faces, and this is the proper way to do the testing. So you have to use a test reference cord. If it goes bad, don't use a normal cord. Request get another set. Makes a big difference between a loss. We are talking about here, remember, every 3 dB, half of your power is gone. So all these little things makes a big difference. And also, you gotta remember, you're adding, with having variable cords, you're adding to what we call uncertainty. So that means from one time to do the test to the next time to do the test in the same moment, you will have different results. And you don't know whether you have a pass or a fail. So it becomes quite critical to look at these. Okay? And this one just cannot happen. Because you're losing energy. You cannot have zero losses. So again, it has to do with the proper test reference cords in order to get the right results. Make sure that you have the test reference cords whenever you do the testing. Okay? Now, if you remember, before I did what we call 3-jumper referencing, so that means the uncertainty is 3 times more than a single jumper reference. Remember, I had 3 cords before, now I have 1 cord. So I'm allowed per standard to remove this guy, push it aside, put my link, add a small cord here, and then do my measurement. Okay? And that will give you the most realistic result. Especially when we were talking about, especially in the multimodal world, which is, variabilities are just way too much. So always, again, you have to use the right set referencing. Set reference always in a 1-jumper or B method in order to get the right results. If you do the 2-jumper or 3-jumper, your uncertainty is higher, your results are unpredictable, and your variability is higher. Yes? Doesn't matter. If you're using direct cable, it depends on how long your cable is. If your cable is, let's say, 2 kilometers, 3 kilometers, then the contribution of the connectors are minimal. Then you can do a 3-jumper reference. But we still recommend 1-jumper reference. Okay? When the number of connectors are a lot, okay, and you're running shorter distances, we recommend 3-jumper reference. Okay? Matter of fact, the 3-jumper reference is called B, and then the 3-jumper reference is called C. I always remember B is for building, C is for campus. Campus, longer distances, no connectors in between. So you can run 3-jumper referencing. Okay? But within the building, definitely run 1-jumper reference, method B. Okay? And this is what you can see. So TIA, this is the number 1 that they are recommending versus this one, which is 2-jumper, which is method A, and then C, which I told you, which is the basically the 3-jumper referencing. And 1-jumper method has the most accurate results because the number of variables in it is less. It's natural. Okay, the other thing that is in the TR42, that is, or TSE 140, excuse me, Technical Service Bulletin 140, is they're saying that, especially in the multimode world, what happens is that the light that is coming out of LED, which is a standard for the light source of any tester, fiber optic certification tool, you have to stabilize the light. The variabilities are just too much. So what you use is what we call a tuned down drum, or what we call a mandrel. What it will do, the mandrel, it will take the higher order modes out, so you have a uniform light coming through the the ferrule of the tester itself. Okay, or of the, sorry, patch cord itself. So the light that comes out of the patch cord is uniform. So that means, let's say, for example, if you measure without the mandrel, the light, let's say one time is 1 dB, next time is 1.2 dB, next time is 1.6 dB, next time is 1.8 dB, just too much variable. So you don't know whether you have a pass or a fringe when the light goes into the link. Whereas when you put a mandrel, it always stays at 1, 1.01, 1.99. It's very close, so the variability is a lot less on the light that comes out for measurement. So you need to have a mandrel wrap, okay? So what we say, the mandrel, it takes the loosely bound higher order modes out. This is for multi-mode. Single mode doesn't have a mandrel. Okay? And this is what happens. So basically what mandrel does is, you can see the light that comes out of a LED is overfilled. So what we do is, in order to control it, we bend it so the extra lights will go out, so the lower order modes will stay within the fiber itself. I'm losing my light here. It's okay. Anyway. Okay. Now, challenges in 10, 40, 100 gig testing. This is coming. This is knocking on the back of your home. From 2000, this is what they're talking about. You will have quadruple links which will be running on 40 and 100 gig from 2014 to 2020. So it is inevitable that you will have to deal with it. So it's better to understand it now. Always when you have a challenge, it's difficult, but in order to understand, in order to basically win it, or overcome and surpass all the problems, you need to understand that. Once you understand it, then you can go. Sorry?
Sorry, Mike, let me say something. For the people who are in the data center business, the Cisco have launched one of the Nexus switches. Nexus switches are meant for data centers, and Nexus switches being launched now with 40 gigabit interface.
So I already mentioned.
40 gigabit is in the field today. So dealing with it, you have to start dealing with data center build-ups from today to be ready for 40 gig. 40 gig is not something that will come in the next couple of years. No, it is existing today. So we have some cable vendors here who can share with us their experience about it, but 40 gig is there.
Okay.
We need only one way to do it, which Mike will continue discussing.
I already told them that there's plenty already out with the new modules running at 100 gig. Now, one of the things that will happen, especially from the testing side, now we're focusing on the testing side, I want to show you the difference between when you have a fiber misalignment and when you have a LED light source on your tester versus when you have a VCSEL on your tester. Okay? You can see in both cases, I have misalignment between my fiber on the left and the right. Do we agree on that or not? Clearly there is a misalignment. The only difference is that here I have an overfilled light source or LED, and here I have an underfilled light source which is a VCSEL, right? Now, how does the light source power meter work? The light source will send the light across, the power meter will measure what is received, then the light source will tell how much power I have injected. So then you can see the dB loss, right? This is the way the light source power meter works. Now, this one, of course there's more light. It will go through, part of it gets stuck here, part of it will go into the cladding because it's overfilling, and part of it goes to the misalignment issue. So you read, let's say 3 dB loss. Okay? Now, let's take a second example of a tester which has a VCSEL. Since it is underfilled, it will go through, and if it is enough misalignment, it will not hit the misalignment section. So the light will go through, then the light is measured from the receiver side, from the meter side, and then the light source will say, I send this much power. Right? So this one will say, oh, you have 2 dB loss, which is a lot less than the 3 dB loss. So you can clearly see here that this guy, if you had a VXLAN light source on your tester, wouldn't have even detected the basically misalignment. So you must have an LED on your light source for the testing side. It is mandatory. Don't go with the VXLAN one. You will get what we call optimistic results. You will be happy that you have a pass, but when the customer calls you and he says, my database is slow, then you have to go again and scratch your head and take the same tester over, and it says, oh, still you have the same. You say, oh, and you cannot figure out what's going on. Because the guy is saying the network is slow, and then you will see the result shows something different. Right? Then you point your finger to the database guy. You say, oh, the problem is the application. Whereas the problem is you didn't use your right tester. Make sure that the tester is LED. Okay, now, when we talk about 100 gig, 40 gig, you really have to scratch your head, what do we have to use as a standard? Okay, so I will walk you through a typical example, and then we'll see what the outcomes will be, and what challenges we have, and what the standard or evolution of fiber optic has driven us into. Okay, now if you look at here, let's say for example, you want to test based on application standard, which is not distance dependent, it's not per connector, it says maximum you have 300 meters for all 300. And then it will tell you for 850 nanometer, you have 2.6 dB maximum allowable loss. Remember this number because we're going to come back to it. Okay? Then you go here and you say, okay, for a channel for all 300, I will be having 2 wavelengths between 2.55 dB and 3.25 dB, depending on which wavelength we have. All right? So we go one step further, and we already seen that this is the standard, so I'm not going to talk about the standard. We go one step further, and then we go and we say, okay, for 40 gig, for example, 40 gig SR4, you can see that for 100 meters